So let's go ahead. Some of this we've actually already covered. So for example, this one right here, I'm just going to go over it. This is the one that I call the vampire things. Technically it's called a doublet of doublets. Yeah.
So we would need to know how to do that second benzene ring structure.
This one?
Oh, that's what that is?
Yeah. Yes. Because it's just the fact that many times it'll look something like this. And it says it integrates to 5. Because, I mean, there's only one way, and in fact, it's the only way that I can think of, on relatively small compounds to have anything that has 5 hydrogens on it. Okay? Or, I mean, in theory, you could have something that does 10, like if it's a multiple of 5. So, for example, just let me put this on the video too, so that way. Okay, whoops. If we had something that looked like this, and unfortunately, I can't find my pen, so. Oh, that's supposed to be a benzene ring. Sorry about that. And it's got this. That may not be the best example. Oh, here, wait just a second. Instead of making that one a double bond, oh, come on now. Let's make that a single bond with a hydrogen here and an OH. I wanted to point this out, and the reason why is that then don't be alarmed if it has signal integrated to 10, because you have 2 identical 5 hydrogen, I'm making that word up, 2 identical benzene rings that are in 5, but once again, it's a multiple of 5. Okay. So this was the whole, they call it leading doublets. I call it vampire teeth. So you can kind of see the idea. They go through the entire theory behind it. On your own, you can look into it. But I would never ask you to explain in your own words the theory behind the reason why it happens. That these more complex, and the reason, I mean, in a nutshell, the reason why is that the hydrogens affect each other just a little differently since they're in slightly different environments. Okay. So that's where we get these complex ones. Also, for example, here's another one where we have the fact that these 2 hydrogens are going to be slightly different from each other, and so they're going to affect this one slightly differently. Okay, because we have one that's on the same side. We haven't covered double bonds yet. We have one that's on the same side because that would be cis to the cis position, and then we have one that's on the opposite side or the trans position from it. And so they're going to have just slightly differences in energy, and it can make the splitting be a little bit more complex. Just want you to be aware of that, especially whenever you're working on your lab reports and you're coming across some of those that are more complex. But I wouldn't, on an exam or a quiz, like if doing the kind of thing that we just did on the board, I wouldn't ask you to draw something that had, doublets of doublets and things like that. Okay. Okay, I do want to spend some time talking about alcohols. You would expect alcohols to be way down here, right? Because it's the hydrogen directly on the oxygen. The oxygen's so electronegative. But it's not quite that simple for both alcohols and amines, but especially and carboxylic acids. Okay, carboxylic acid is still way down there, but alcohols, what you're going to find out is they can actually be a whole wide range. All right. So first of all, you would also expect the alcohol to cause the neighboring atoms, hydrogens, to split to a doublet. However, this does not always happen. In fact, more often than not, it doesn't. And so I wouldn't expect you to say, oh, it splits. Okay, they're showing you one example where it does, but more often than not, it doesn't. And that's because of the fact that proton doesn't stick around whenever you're in water. It doesn't stick around long enough for it to cause the splitting. Okay, all right. So this is what that's saying. What happens here is that proton, it's called solvent exchange. especially the higher the temperature you go, the easier it is for it to pop off and the hydrogen from the water to pop on. So since they're constantly coming on and off, they themselves don't split, and they don't affect quite the same as what you would expect. Okay. So that's what they're saying here is it is not split. It's always going to be, for all intents and purposes, for us, I would expect you to say that it's going to be a singlet. That doesn't say that sometimes that it doesn't split and on ones that are non-solvent exchangeable, or if you go to cold enough temperatures, but we'll just say that under standard temperatures that they don't split and they don't cause the adjacent protons to split. But because of this, they also have a really broad shift. So that makes it a little bit more difficult, and I really wish that they would have shown an example here, but they don't. So let's say, for example, and I don't know what, let's say that we had a proton NMR that looked like this. Of course, we have a TMS signal for a 0. It goes to 10, roughly. Okay. No. I don't know. Let's say we have, I'm trying to think of an example now off the top of my head, but let's say that we had multiple peaks. Okay? And we don't know. We know that there's an alcohol, but we don't know, and I didn't. And, this one went to, I'm just going to call it X because that's not important for the integration. We know that there's an alcohol present, but we know there's only one alcohol. Okay, so then the question becomes, which peak is the alcohol peak, since it can vary so much? So what they do is they run the spectrum, and they would run it like this in water. Then they take it and they run it in what they call heavy water, which instead of H2O, it's D2O. Well, the D, the deuteron, is silent. Well, since what's going to happen is since the spectrum only looks at hydrogens, when you rerun that, one of those peaks will disappear. If it's an alcohol, carboxylic acids also do this, okay? But if it's an alcohol carboxylic acid, it's going to disappear because of the solvent exchange, because the D replaces the H on the alcohol or the carboxylic acid. And so, therefore, if all of a sudden one of these disappeared, oh, it won't let me erase now. Let's say that one disappeared, so I don't want to have to redraw. Then we would know, okay, that was the alcohol one. The other one would be a CH group or something like that, okay? And that's just what I wanted to point out, and that's what they're talking about in that previous slide. Oh, I don't want to go, that one, yes. You don't see the differences for an axial and equatorial because it's exchanged. It moves around. Okay, this is really what I want to point out. You want to get down to C13. Hopefully you know, because you're supposed to have already read this part in the book. I just wanted to explain it. They use a couple of standards, one of which is TMS, which we've been using. That's how they dictate what the 0 position is. But another one that they like to use is that one that's that deuterated trichloromethane. That's what that means. Because they know that it's a known position, so it's kind of like fine-tuning it, so to speak. One thing I want to point out in the beginning, instead of going from like 0 to 10 or 12, it goes from 0 to like over 200, like 200 to 250. That's the big difference. Or that's one big difference. And this one, I would expect you to be able to name this one. There's 1, 2, 3, 4, 5. So that's going to be 1 chloropentane. I'm going to try to blow this up myself, because this is the part that's important. One big thing that you should notice right off the top is they do not split, right? So you would think if it was true, if this was similar to the proton NMR, you would say, oh, this is, one carbon touches 2 carbon, so maybe it's going to be a triplet or something like that. They just don't split like that. If you notice, these will all be these peaks. They also don't integrate. So it doesn't tell you the same type of information that a proton NMR does. What it does tell you, and what it's so good at, is it's much more sensitive to the chemical environments, to where, now let me go back. If you notice, even on a relatively small NMR, every single one of these carbons is slightly different, and we get a peak for each one of them. Whereas sometimes with proton NMRs, especially things, if you have a weak magnet, if it's something really, really long, you won't be able to tell the difference between some of the protons that's in the middle of the compound, because they all start to blend in together unless you get to a really, really high magnet. With the C13 NMR, we don't have that issue. Another one drawback is, if you remember, 99% of all hydrogens are protons. However, it's a very small percentage of all carbons are C13. Most carbons are C12. So C12s you don't see on that. That's the reason why we don't see some of the same type of patterning, the splitting, and things like that that you would see with the proton NMR. Okay, this is just what they're going to say. I just said it as well. So it's just letting you know C13 is something you can see. However, C12 is silent. And so the natural sample for C13 is very, very small. But it's high enough that you can still run samples, but you can't see the same type of splitting and integration and things like that. Okay? They take longer since the signal is weaker. And as I mentioned, they don't. But they do say, look at the range. You go way, it's very, very high. Okay. I just want you to know the broad strokes here. And it's very similar to what we've seen in the past. Methane is going to be really close to zero. Primaries are the next. Then as you go downfield, you get secondary, tertiaries, and then finally quaternaries. Okay. And then finally, I shouldn't say finally because I haven't. Okay. The hybridization. So electronegativity affects it, and so does hybridization. So obviously the more electronegative, similar to hydrogens, the more electronegative it is. That's why they're trying to show you this color. The further downfield it will be in the C13 NMR. So fluorines will cause it, and it's also additive, just like before. Okay. The further away that the fluorine, whatever it is, then the less the effect will have. And that's the same thing that we've seen with hydrogens. sp2s are going to be less shielded than an sp3. However, once again, that the triple bond does something that's kind of anomalous to that, where it's more shielded than what you'd expect due to the fact that it's got the two sets of pi electrons instead of just the one set. So remember when we drew out the cartoony looking ones, the double bond only has one dumbbell, but when you do a triple bond, it's got two sets of dumbbells kind of surrounding those carbons, if you want to think of it that way. All right. And once again, the integration do not tell you the number of carbons. However, each peak goes to one, tells you, it goes to the number of carbons, and you get the number of peaks, tells you the number of carbons that are chemically non-equivalent. Okay, so that's why if we look at this one, once again, just ignore that. That's just one of the standards. Just like if they had drawn in the TMS, you would ignore it. But this one, in the proton NMR, we wouldn't be able to see necessarily as good a separation as what you would here for the number of protons. But here, first of all, we don't see that one at all because there's no carbon there. But we have the 6 carbons for the benzene ring and the 1 carbon for the methyl group. So we have 1, 2, 3, 4, 5, 6, 7. And so a lot of times you want to run the C13 and the proton NMRs together because it helps you. Like if we had done that in this example that we worked out before, you would have figured out that there were 3 carbons that were chemically equivalent. because you would have actually fewer number of carbon peaks than what you would expect. You would not see 7, you would have seen 2 fewer, because of the fact that 3 of them are identical. Okay.